On the northern coast of Maine, there is a cedar fishing shack that faces salt wind for 8 months of the year. Its boards have gone silver, then brittle the way untreated wood does when sun and moisture cycle long enough. It already priced replacement siding and was preparing to schedule a crew. Instead, he mixed a small jar of 3 common liquids from the local hardware store and wiped one wall by hand. Minutes, the gray surface darkened to the color it had decades
It's a
earlier.
resurrection.
Not painted,
The forbidden
not
wood
coated in a
restoration
glossy film.
liquid brings
The wood looked
centuries of
hydrated,
history
as if it
back
had
to
been
life.
stored indoors all along. The cost of that mixture was negligible compared to the labor estimate he had received. No sanding discs. Pressure washer, no specialized sprayer. Just controlled chemistry applied directly into the grain. What happened on that shack is not new, and it is not a miracle. It is a drying oil reaction that has been understood for more than a century and used for far longer. Before discussing performance or cost, it is necessary to understand that this is not about hiding damage. It is about altering the condition of the wood fibers themselves. That distinction changes everything. Long before modern coatings existed, coastal builders in Scandinavia treated pine hulls with pressed seed oils to slow rot in freezing harbors. In rural Japan, carpenters working on temple gates used plant-derived oils to condition exposed beams that faced monsoon humidity year after year. In parts of Eastern Europe, farmhouse doors were maintained with oil extracted from flax and hemp seeds, seasonally as part of routine upkeep rather than as a major restoration event. These practices developed independently, separated by geography and language, yet converged on the same principle of penetrating oil that reacts with air and becomes part of the wood structure. No shared patent, no industrial branding, no unified instruction manual. The method persisted because it solved a structural problem. Wood is porous, and any long-term protection must account for that porosity rather than ignore it. By the late 19th century, industrial chemists in Europe formalized what craftsmen had already observed. When certain plant oils are exposed to oxygen, they form a resilient polymer network. That understanding eventually led to large-scale manufacturing of oil-based floor coverings and protective finishes. But the underlying chemistry had already been tested informally for generations in barns, bridges, and tool handles. The continuity across cultures is not romantic nostalgia. It is evidence of functional convergence. When different societies, facing different climates, arrive at the same treatment method, it suggests the mechanism is reliable. Occasions the timber species changes, the tools change. The principle does not. The effectiveness of this mixture begins with boiled linseed oil, drying oil derived from flax seed that contains a high concentration of polyunsaturated fatty acids, particularly alpha-linolenic acid. These molecules are reactive in the presence of oxygen. When the oil is applied to wood, it does not remain as a surface film in the way acrylics or polyurethanes do. It moves into the capillary structure of the timber from the microscopic channels that once carried water through the living tree. Once inside those channels, the oil undergoes autoxidation. Oxygen from the air reacts with the unsaturated bonds in the fatty acid chains. Those chains begin to cross-link, forming a flexible polymer network. This process converts a liquid into a solid matrix within the wood fibers themselves. The result is not a shell sitting on top, a structural modification inside the grain. The wood becomes internally reinforced while retaining the ability to expand and contract with seasonal humidity changes. The addition of distilled white vinegar serves a preparatory role. Acetic acid loosens oxidized surface layers and helps dissolve accumulated grime without aggressively stripping intact fibers. It effectively clears access to fresh wood so the oil can penetrate more uniformly. The third component, natural gum spirits of turpentine distilled from pine resin, reduces viscosity. Thinning the oil allows deeper penetration and more even distribution before polymerization begins. Combined in equal proportions, the mixture becomes a transport system. The solvent carries the oil into the timber. The acid prepares the surface. The oxygen-driven reaction locks the structure in place. Nothing about this chemistry is speculative. It is a controlled oxidation process that has been documented for over a century in coating science. Modern synthetic finishes approach the same problem from a different direction. Polyurethane, alkyd varnish, and lacquer are designed to form a continuous film on the surface. When properly applied, they can create a hard, abrasion-resistant layer that initially appears flawless. The limitation is structural. That layer remains external. Ultraviolet exposure, thermal expansion, or mechanical stress creates a crack in the film. Moisture can migrate underneath. Water is trapped below. A non-breathable coating, peeling and blistering follow. A penetrating oil system behaves differently. The polymerization occurs within the fibers. There is no discrete shell to delaminate. Minor surface wear does not expose a boundary between coating and substrate. It simply reveals more conditioned wood beneath. In comparative testing published in coatings literature, drying oils have demonstrated significantly deeper penetration into open, grain species than film, forming synthetics. Depth of penetration is not cosmetic. It determines how the material responds to stress. On exterior cedar siding, the difference becomes visible within 2 to 3 seasons. A film finish often requires sanding before reapplication because adhesion depends on mechanical bonding to the old layer. Treated surface can be refreshed with a thin maintenance coat after basic cleaning, since there is no brittle film to strip away. On interior hardwood, the oil produces a satin finish that diffuses light, rather than reflecting it sharply. The aesthetic is secondary. The structural resilience is the primary variable. The comparison is not about declaring one category universally superior. It is about recognizing that penetration, base systems and surface, film systems solve the durability problem through fundamentally different mechanisms. Understanding that distinction allows informed selection rather than habitual repetition. The shift towards synthetic film finishes in the mid-20th century was not driven solely by performance. Aligned with manufacturing efficiency and scalable branding, petrochemical resins could be produced in controlled batches, tinted, packaged, and marketed as differentiated product lines. Faster drying times reduced labor hours. Higher material costs supported higher margins. None of this required suppressing older methods. It simply made newer ones easier to scale. A business perspective, a finish that requires complete stripping and refinishing every few years generates predictable demand. A penetrating oil system that can be refreshed with a light maintenance coat does not create the same repeat service cycle. Contractors are compensated for labor and scheduling complexity. Manufacturers invest in formulations they can trademark and distribute exclusively. Natural drying oils and pine-derived solvents cannot be patented in their raw forms. That limits the ability to build proprietary advantage around them. In the United States, the broader home improvement sector exceeds $200 billion annually. Exterior wood maintenance alone represents a meaningful share of that total. When homeowners search for solutions, the first results are typically branded systems bundled with accessories and application tools. This is not a coordinated effort to conceal alternatives. It is an outcome of advertising budgets and supply chain leverage. Simplicity rarely receives sustained promotion because simplicity offers limited opportunity for differentiation. The economic dynamic does not invalidate modern coatings. It explains why certain low-cost, proprietary methods gradually lose visibility. Markets reward products that can be packaged, trademarked, and distributed at scale. Basic chemistry available in bulk containers does not fit that model comfortably. This mixture is effective within defined boundaries. It is not a structural repair system. Fibers have decayed to the point of softness. No oil will reverse fungal damage. Severely rotted sections still require replacement. Penetrating oils condition and stabilize. They do not rebuild missing cellulose. Curing time is another practical constraint. Bold linseed oil contains metallic drying agents that accelerate polymerization, but temperature and humidity still matter. Damp conditions, full curing may extend beyond 48 hours. Applying heavy coats to compensate for impatience can leave a tacky surface. Thin, controlled applications produce better long results than saturation. Color shift must also be acknowledged. Drying oils impart a warm tone. Species such as walnut, oak, or cedar, this enhances grain contrast. On pale woods like maple or birch, yellowing may be noticeable over time. That aesthetic effect should be anticipated rather than treated as a flaw. Also, a safety rule that cannot be ignored. Rags saturated with drying oil generate heat as oxidation occurs. When left crumpled, that heat can accumulate and, under certain conditions, ignite. Proper practice requires either laying rags flat outdoors to dry fully or submerging them in water inside a sealed metal container before disposal. This is not a rare edge case. It is a well-documented hazard associated with all drying oils. Used correctly is stable and predictable. Used carelessly, it introduces avoidable risk. There is another dimension to this discussion that has little to do with chemistry and more to do with habit. Over time, homeowners internalize the idea that visible deterioration requires professional intervention. Boards signal expense. Peeling finish signals a service call. Is to outsource the problem before evaluating the mechanism behind it. When a process appears technical, branded or specialized, it carries authority. When it appears simple, it is often dismissed as incomplete. A mixture of seed oil, mild acid, and pine solvent does not look advanced. It does not come with a certification card or a proprietary applicator. Yet the underlying reaction is the same oxidative polymerization that forms the backbone of many commercial oil-based products. The difference is presentation, not chemistry. There is also an inertia effect. Once a homeowner has paid for professional refinishing, the repetition cycle becomes normalized. Scheduled maintenance every few years feels responsible. Interrupting that pattern requires both information and confidence. The barrier is rarely technical capability. It is uncertainty about whether a simpler approach is credible. Understanding the mechanism reduces that uncertainty. When the process is demystified, the decision becomes analytical rather than emotional. The wood is not failing because it lacks branding. It is drying, oxidizing, and losing internal oils. Reintroducing a reactive drying oil addresses that condition directly. Look at weathered timber. After understanding the mechanism, the framing changes. Instead of seeing a surface that must be covered, you see a porous material that has lost internal resilience. Instead of assuming deterioration equals replacement, you evaluate whether the fibers are still structurally intact. If they are, the solution is not concealment. Reconditioning? This shift moves maintenance from episodic repair to ongoing stewardship. A penetrating oil system encourages small, periodic interventions rather than large, infrequent overhauls. A light annual coat applied in controlled conditions prevents the need for aggressive stripping later. Remains breathable. The protective network remains internal. The cycle becomes predictable and low cost rather than reactive and expensive. Structural thinking also clarifies material selection. Dense hardwoods with tight grain behave differently from open grain softwoods. Exposure conditions matter. Horizontal deckboards experience standing water and ultraviolet stress. Vertical siding sheds moisture more efficiently. Once you understand penetration depth, polymer formation, and expansion tolerance, you can tailor application frequency rather than defaulting to generic schedules. The broader insight is that many maintenance problems are misframed as surface failures when they are actually internal depletion issues. Addressing the internal condition first often produces longer, lasting stability. The practical takeaway is straightforward. 3 accessible materials, combined in equal proportions, create a penetrating treatment grounded in established chemistry. 1 part boiled linseed oil, 1 part distilled white vinegar, and 1 part gum spirits of turpentine. Mixed thoroughly in a sealed glass container, applied along the grain with a clean cloth, allowed to absorb, then wipe back before curing. A second light coat after 24 hours deepens protection. Maintenance becomes incremental rather than disruptive. This approach does not eliminate the need for professionals in every scenario. It does not replace structural carpentry, nor does it override cases where modern high-build coatings are appropriate. What it does provide is optionality. When wood is weathered but intact, you have a method that is low, cost mechanically sound, and repeatable without specialized equipment. Autonomy in maintenance begins with understanding. Once you recognize how oxidative polymerization works inside the fibers, the gray deck or faded siding becomes a solvable materials problem rather than an invoice waiting to happen. The decision to use this method is not ideological, it is analytical. Evaluate the condition of the wood. Thin coats, observe the result, adjust as needed. If this explanation clarified the structure behind a common household issue, continue exploring and apply the same analytical lens to other systems around you. Practical knowledge compounds over time, and small corrections in understanding often lead to disproportionate savings in cost and effort.